Chemical properties of phenol. First one, acidity. Phenols are fairly acidic and they can react with alkali metals such as sodium to form salt, sodium phenoxide. Similarly, these phenols can react with aqueous alkalis like sodium hydroxide to also form salt, sodium phenoxide. These two reactions indicates the acidic nature of phenol. This acidic nature of phenol is due to the formation of stable phenoxide ion. That is, when phenol removes H plus or undergo ionization, we get an ion called phenoxide ion and H plus. This phenoxide ion is more stable. That's why phenol can easily remove this H plus. So that's why this phenol shows acidic nature. This acidic behavior of phenols clearly explained as due to two reasons. Now, what are the reasons? Let us check. Consider the resonance structures of phenol. Here these are the different resonance structures of phenol. These are the different resonance structures of phenol. Now consider the resonance structure of phenoxide ion. This is phenoxide ion. This is the resonance structure of phenoxide ion, and this is the resonance structures of phenol. Now let us compare the resonance structures of phenol and phenoxide ion. In the phenoxide ion, the negative charge is spread or dispersed throughout the Benz ring and there is no charge separation. But here, in the case of phenol, the resonating structures containing charge separation. Here is a charge separation. Similarly, here this structure also contains charge separation. This structure also contains charge separation. So, in the resonating structures of phenol contain charge separation, or due to resonance of phenol, there is a chance for creating charge separation. Due to this charge separation, their stability is low, and consequently their contribution to the total structure of phenol is also low. Hence, the phenol molecule is less resonance stabilized than the phenoxide ion. Phenol molecule is less resonance stabilized than the phenoxide ion. So, the phenoxide ion, which is formed by the ionization of phenol, is more stabilized than phenol. So, phenoxide ion is more stabilized than phenoxide ion is more resonance stabilized than this phenol. The fact that the phenoxide ion is more stable favors the ionization of phenol with the release of proton. So, that's why the phenol is acidic, or phenol shows acidic nature. Phenol shows acidic nature. Phenols are much more acidic than alcohol, and less acidic than phenols are less acidic than carboxylic acids. Phenols are much more acidic than alcohol and less acidic than carboxylic acid. Consider the ionization of general alcohol ROH. It ionizes to RO minus plus H plus. And the ionization of phenol. O minus plus H plus. Here you can see that when a general alcohol ROH ionizes to alkoxide ion RO minus, and the phenol ionizes to phenoxide ion and H plus. This phenoxide ion already discussed or already told that this phenoxide ion is resonance stabilized. But here alkoxide ion is less stable because this negative charge is concentrated or localized on this oxygen atom only. But here in the case of phenoxide ion, this oxygen atom is delocalized throughout this benzene ring. So the ion which is formed by the ionization of phenol, that is phenoxide ion, is more stable than that of this alkoxide ion. That's why the phenols are much more acidic than alcohol. Next, effect of substituents on acidity of phenol. Effect of substituents on the acidity of phenol. Effect of substituents on the acidity of phenol. Just take the ionization of phenol. O minus plus H plus. This is phenoxide. The acidity of phenol is due to the formation of stable phenoxide ion. When a group or substituent which has the power to enhance the stability of phenoxide ion increases the acidity of phenol. So when a group or a substituent which has the power to enhance the stability of phenoxide ion increases the acidity of phenol. Now let us check an example. NO2. It is an electron withdrawing group. EWG means electron withdrawing group. Let us check the para-nitrophenol. Is para-nitrophenol. Ionizes plus H plus. It is para-nitrophenoxide ion. Now let us consider the resonating or resonance structures of this para-nitrophenoxide ion. Shifted to here. So these are the different resonance structures of para-nitrophenoxide ion. So here this NO2 group enhances the stability of phenoxide ion through the dispersal of negative charge. Para-nitrophenoxide ion resonance stabilized than phenoxide ion. That is why para-nitrophenol is more acidic than phenol. So electron withdrawing group like NO2, COOH, CHO, Cn. Electron withdrawing group like NO2, COOH, CHO, Cn, cyano group increases the acidity of phenol. Electron withdrawing group present as a substituent in phenol increases the acidity. Now let us check the position of electron withdrawing group. How the position affect the acidity, how the position of electron withdrawing group affect the acidity. Just take the resonance structures of phenoxide ion. just look here, this negative charge is the negative charges were coming this ortho and para positions. Ortho and para position corresponds to this O minus ion. This negative charge is coming this ortho or para positions. Ortho or para positions. This effect is this effect means the increase in acidity, or simply this effect is more pronounced when the electron withdrawing group present on ortho or para position. Ortho or para position. The increase in acidity effect, or simply the effect, is more pronounced when electron withdrawing group present at ortho or para position. Ortho or para position. Ortho or para position. Because of the greater stabilization due to dispersal of due to effective dispersal of negative charge. Effective dispersal of negative charge. Now let us check the acidity of different nitrophenols. Let us check the acidity of different nitrophenols. Is orthonitrophenol, metanitrophenol, pyranitrophenol, simply phenol. Let us check the acidity of this molecule. The acidity of this molecule is in the order paranitrophenol is the first one, that is high acidic character. Then second one orthonitrophenol, then metanitrophenol, then phenol. So the acidity is high in the case of this paranitrophenol. Or the electron withdrawing group which is present on ortho or para position, this acidity is increases. Acidity will increases. Here this paranitrophenol is slightly more acidic than this orthonitrophenol, because in the case of orthonitrophenol there is a chance for creating hydrogen bond between this OH and NO2, intramolecular hydrogen bonding. So this hydrogen atom of this OH is tightly attached. That's why this paranitrophenol is more acidic than that of this orthonitrophenol, because this here is there's a chance for creating intramolecular hydrogen bonding. So the removal of hydrogen is comparatively difficult. That's why paranitrophenol is more acidic than that of this orthonitrophenol. Now, an increase in the number of electron withdrawing substituents increases the acid strength. Just take an examples. This is 2,4,6 trinitrophenol is more acidic than that of 2,4-dinitrophenol, more acidic than that of paranitrophenol, more acidic than that of phenol. So an increasing number of electron withdrawing substituents or electron withdrawing group increases the acidic strength. Increases the acidic strength. Next, how this electron releasing group affect on the acid strength of phenol. Electron releasing group, ERG. How this electron releasing group affect the acid strength of phenol. An electron releasing group such as alkyl group or 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 NH2. This alkyl group or alkoxy or NH2 groups are present on the phenol, then the acid strength decreases. Acid strength decreases. When electron releasing group present on phenol, the acid strength decreases. Because an electron releasing group strengthens the negative charge on this phenol ring. That's why there's a destabilization occur. So orthocrosol is less acidic than phenol. So an electron releasing group present on phenol, acidity decreases. So we concluded that, or we generalized that an electron withdrawing group EWG increases the acidity of phenol. Increases the acidity of phenol. Similarly, electron releasing group or electron donating group decreases the acidity of phenol. So electron withdrawing group increases the acidity. Similarly, electron releasing group decreases the acidity.